We are going to add another operation to our list of function operations, joining, addition, subtraction, multiplication, and division. The operation that we're going to join in with those two is called a composition, or with those four, excuse me, is called a composition. In a composition, and you can see it from the example right here, in a composition, one function serves as the input of another. You'll notice here that f has g inside of it. Sure, g has 3 inside of it, but f has g inside of it. So we are going to first evaluate g at 3 and use that number as the input for f. When we work with compositions, we work our way from the inside out. We evaluate the innermost function and we work our way to the outside of the function. So we're going to start by evaluating g of 3. Normally this is done as sort of like side work, like you're going to have it happen over here, where you're not going to get it bunched up with all of this work because you don't want to have to keep writing f of this long expression and then try to simplify it down from there. So g of 3, and let's use our function g, we're going to say 3 squared minus 3, which is 6. And because I evaluated g of 3 as 6, I'm going to use 6 as the input for f after I determine that number. So I'm going to use 6 inside of f, and I'm going to have 2 times 6 plus 1, which is a grand total of 13. So f of g of 3, and that's how we read that, f of g of 3 is equal to 13. And we get that through the use of both of those functions. Same thing happening down here. We're going to start with f of 3 this time. You'll notice that f is on the inside now. We're going to start with f of 3, and that's simply 2 times 3 plus 1, which is 7. That means that 7 is going to be our input for g. 7 squared minus 3. 7 squared is 49. That leaves 46. So g of f of 3, and again, that's how that's read. You just read it from the outside in. We do the work from the inside out, but we read it from the outside in. G of f of 3 for a grand total of 46. Now, this numerical use of a composition is interesting in the sense that it allows us to use the inputs into one function, creating an output that becomes the input of another function. But what happens if we don't really have any inputs? What happens if we just have the functions themselves? Well, there's also an algebraic application of the compositions of functions that goes beyond just the numerical use of the composition. Here you'll notice that there's no actual input. So the question becomes, well, what am I going to input to g? And the truth is you're going to input x. You're going to take this expression, x squared minus 3, the actual function for g, and that is what you're going to use as the input for f. So inputting into f is going to go x squared minus 3. So looking at this very carefully, we see that f's input is normally x, but instead of putting an x in, we're going to put x squared minus 3. Everywhere we see, remember what function notation is. This is a signal for the independent variable. It's telling you what to look for over here. So if this is telling me to look for an x over here, and I see that 1x right there next to the 2, that's where I'm going to put g. I'm going to put g so that it is positioned directly next to the 2. So 2, all of g, and then the plus 1 that's at the end of f. And so I used g as my input for f. And when I use g as my input for f, I end up with this function over here. Now, obviously, you could multiply that. You could distribute it. You could clean it up a little bit. For the purposes of this exercise, though, we're going to leave it like that so you can really see that idea that it's just being input into where x was. You'll notice our second example is the exact same idea, just reversed. Instead of going f and g, it's going g and f, g of f of x. So now we're going to have g, and the input of g is going to be f. So wherever we see an x, we're going to put a 2x plus 1. So let's look at g again. Here's g. I'm going to get rid of some of this so we can see it a little better. Here's g right here. I see my independent variable notification. I see the independent variable over here. Both of those are getting replaced with 2x plus 1. So I've run into the x squared. I'm going to replace that with 2x plus 1. I'm going to make sure I square it because that's what's happening to the independent variable in the original equation. And I'm going to finish with the minus 3 that's at the end. Again, we could call back some of the work that we did in previous courses, the work you've done in previous courses, to multiply out this perfect square and subtract the 3. But again, we like to just see that substitution for now. You can compose a function with itself, and the same logic will hold. 2x plus 1 is now going to be the input into 2x plus 1. So wherever we see the independent variable in f, we're going to replace it with a 2x plus 1. So we're going to say 2x plus 1, and another plus 1. This 2, part of the original function, this 1, part of the original function, this 2x plus 1, all coming from that input. And then the same thing down here in g. We're going to say g of g, which is g of x squared minus 3. We're going to look at g again. We're going to see g's independent variable. That's where we're going to put x squared minus 3. That's going to get squared because of the original square in the function and the minus 3 at the end. So again, we have the square from the original g. We have the minus 3 from the original g. And we have this input in the place of the x because that's what the composition suggested.